and good morning, ladies and gentlemen. Good to see you all. I just want to go through you for a few minutes this morning about some of the installation activities regarding transportation of offshore modules and jackets. Some of the vessels that we use, some of the stability enhancements that we add to these vessels, some GZ curves, and then some incidents of damage. There are three main phases in the installation of an offshore structure or the delivery of a module from yard to another onshore site. So that's the loadout, the ocean transport, and then a float over or lifting offshore or a load in back at the final location. So this is the side loadout. We've got skid rails here on the shore, skid rails on the transport vessel, and the module in this case is either pushed on or pulled on. The key elements to this are the strength of the ship, the tide, the water depths, and then the stability. Generally with these types of loadouts, we're not looking at GZ curves, but we are looking at GM. So we're looking for a minimum GM of about 1 meter. These vessels have multiple ballast tanks. Some of them have over 60 individual ballast tanks. The typical type of damage case that we look at here is we sometimes get corrosion in the bulkheads and we pump ballast into one tank and the ballast goes somewhere else. And that makes a loadout very difficult. This is a stern loadout. Skidded loadout again, slight slope on it. We've had damage cases that we look at here are where there's misballasting. And there have been quite a few incidents of this, and it's nearly always where one company is doing the pushing and another company is doing the ballasting. And that situation is then made worse if the native languages of the people doing the pushing and the ballasting are different. And you can get into some quite difficult situations when those two things go awry. We'll talk about these a little bit later, but in order to get an increased range of the GZ curve, here are some stability boxes added on the deck. They're not submerged. These stability boxes are not giving you any more GM, but they are giving you an increased range of GZ. And I'll show you some GZ curves in a moment, how that works. We have very big heavy transport vessels for, in this case, the biggest in the world, delivering a very big floating structure itself. We have movable buoyancy tanks at the stern and the bow, and the ship can ballast down to offload floating cargo. In this case, the stability of the floating structure would also be taken into account in the stability analysis and the GZ curve analysis. But of course, you've then got to make sure that the sea fastenings can take the uplift buoyancy forces. This shows another heavy transport vessel where these buoyancy tanks, which would be at the stern for a float on, float off, have been moved up to the bow to be clear for the loadout operation. We sometimes carry out model tests for our structures. In this case, it's a jacket on a launch barge. And here we would take the buoyancy of the jacket legs would be taken account of in the GZ curves. And again, you've got to make sure that the sea fastenings between the jacket and the barge are strong enough to take those uplift forces. We also do wind model tests at a much smaller scale than the wave tests. Just as a matter of interest for you, the top sides of 30,000 tonnes here, a hull of 36,000 tonnes here, the total cost of that package after design and procurement and construction will be $2 billion. $2 billion for the cargo cost. and the ship's another $200 million on top of that. So we use these wind model tests to see what's the wind loading on the cargo and on the ship. Most of our cargo barges and heavy transport vessels are parallel sided so that they can get alongside crane vessels easily, such as this. We tend to operate our offshore installation transport vessels sometimes at very deep drafts, way beyond the load line. So this is a heavy transport vessel designed to carry float-on, float-off cargoes, but in this case it's a float-over of a topsides onto a jacket. And then in order to extract the heavy transport vessel, it's ballasted down till there's only 1 metre of freeboard. We need very good weather for that situation. And we need special permission from the class societies in order to go to such a deep draft at an offshore location. This is a heavy transport vessel, double-ended one, which has just offloaded its cargo. You can see how vulnerable the ship is in this situation to damage or misballasting. So this is a geared heavy transport vessel, big deck cranes, maybe up to 900 tons capacity each, and there's some stability pontoons that it can put into the sea if it needs to increase its GMs during lift. Sometimes on these heavy transport vessels they need to add extra sponsons to provide more buoyancy and more stability. And again, the buoyancy of the cargo will be taken into account here. Here's another heavy transport vessel carrying a semi-submersible, and here you can see these sponsons that have been added to provide more buoyancy and more range of stability. Sometimes owners of vessels decide to add permanent sponsons to their vessels. So this is giving more buoyancy, hence more deadweight carrying capacity, and also a greater range of stability. Many of the heavy transport vessels have these removable buoyancy tanks. So if they're carrying a floating cargo, they have these at the stern. If they're carrying a big module, it's probably stored here at the bow or not taken on board at all. A jacket on a side, on a launch barge with straight sides. You can see the legs of the jacket, they're buoyant. Obviously it has to be buoyant as a launch jacket, and those are taken into account in determining the intact range of stability. There may also be rubber diaphragms on the pile sleeves here to increase that buoyancy, although that's more for the upending of the launch rather than the transportation. This is another straight-sided barge with a module here that's going to be floated over onto a jacket. And you can see the extremely high grillage that we have here. So that high grillage is to spread the weight into the barge, spread the weight of the module into the barge, but also because the jacket will be high above the waterline, that module also needs to be higher. These submersible barges and heavy transport vessels are also used to deliver modules up to about 8,000 tons to LNG sites, refineries, ethylene plants. And for all these cases, we've got to meet the stability criteria, usually of the marine warranty surveyors. So we here see another submersible barge with no propulsion, buoyancy tanks here at the stern, and this can be sunk down into the water for float on or float off of the jack-up in this case. We also have T-shaped barges. This was a launch barge, 51 metres wide, but the gap inside the jacket is only 45 metres. So the bow has been cut down so that it's only 42 metres wide here at the bow. It makes for a very awkward shaped barge, and of course during the tow you get quite big yaw angles during the tow operation. But it's the only way sometimes of getting enough buoyancy and enough stability, and also to get the right width to get the module on top of the jacket. Sometimes we'll load the module onto a small barge if there's limited water depth at the loadout key, and then we'll put it onto a float-on, float-off heavy transport vessel. Another thing that we do to increase the stability of a vessel is this is a crane vessel. And you can see here at the waterline, it's quite a narrow width that enables it to make a fast transit. But when it's doing the lifting, it ballasts it down to this level, and you can see an increased width then, increased stability, which you need for the lifting operations. This vessel's fitted out with a crane now. You asked before about the stability boxes. Many of these heavy transport vessels are really struggling for range of stability. You could put permanent sponsons on the side, but that may mean that we can't do a float-over operation, for instance, or we can't get through a canal. And they also increase the drag during the transit. So what these do is these increase the range of stability only. They decrease the GM initially and then increase the range of stability. And
would it be easier just to limit weathercraft here? Because if you need these sponsons, your barge is at such an angle that your cargo would be in danger anyway.
Well, we have a lot of sea fastings to this.
But you would never want to get in such.
We do. We make ocean transits like this in this situation. If you look in the paper, you'll see the simplified way of saying what allowable range of GZ we need, which is 36 degrees, say, for this size of vessel. But you might find, because the module's up here somewhere, that we can't get to that. So there's a couple of formulas which involve the GM and the angle of roll, which enable you to get to a much smaller range of stability. So you might be down at 25 degrees, 26 degrees range of stability, but that's even with these stability boxes on. It's been used for quite a few ocean transports. So there's been one done recently for a North Sea transformer module. You saw a picture right at the front that came from Dubai and came around to the North Sea. And we had these stability boxes that gave us the range of stability.
Is there any measurement data on these voyages of what are the yield angles that they achieve here?
Yes, there are. Because the GMs are so small, 1 or 2 meters, the angles and the natural roll period is then perhaps 18 or 20 seconds. That then the roll angles are down to 2 or 3 degrees. Yeah. On cargo barges, again, to get some extra buoyancy, extra GM, and then extra range of stability, we also put these sponsons sometimes on cargo barges. They're just put on for a single voyage probably, and then taken off. Probably, knowing the oil industry, probably thrown away after one use as well. Oh well. We'll come back to that one. On the geared heavy transport vessels, they nearly always come with these stability pontoons. They are the complete opposite of the stability boxes that we saw just now, which were to give GZ, range of GZ. These won't give you any increased range of GZ, but they will give you more initial GM. But these stability boxes are only suitable for inshore lifts in very calm weather. And in fact, they're deployed, but they're carried as deck cargo normally, and then they're deployed into the sea just as you need to do the lift. Again, you see here a stability pontoon on a geared vessel, one stored on the deck and one attached alongside. Yes, to answer some of the questions you've been asking, typical righting arm curve. So we're looking, let's say, for between 36 and 44 degrees, depending on whether it's a big vessel or a small vessel. We're looking for this angle of maximum righting arm to be definitely more than 15 degrees and 20 degrees if possible. But not, if you get to 36 degrees here, normally this is only 17 or 18 degrees. For the intact stability case, so we've got our 36 degrees range of stability, and then we're looking to make sure that the area under the GZ curve is more than 40% more than the area under the wind we're turning on curve, up to the point of either the secondary intercept or the angle of down flooding. For an intact stability case, we would use a minimum wind speed of 35 meters per second, maybe 50 meters per second if that's what the client wants, or it's a long sea watch. For our dynamic stability case, we're trying to limit this angle of lull to less than 10 degrees. But and again, we're looking for 40% area under the GZ curve compared to the wind moment curve. But this was with a reduced wind speed of 25 meters per second. What our clients want and what our managers want to know is, in all cases, what is the maximum cargo weight and VCG? In fact, most of our managers don't even want to know about the VCG. So you've got to say, what is the maximum allowable cargo weight? So we produce a simplified VCG curve of cargo and allowable VCG. This is to answer some of the questions you're asking about the stability boxes and so on. So the blue line is the GZ curve for the parallel-sided vessel, normal GZ. If you add sponsons on the side, noting that you're also increasing the drag as well, you've got a much bigger GM to begin with, and you get an increased range of GZ. The grey curve now is with the stability boxes where they're only on the deck. So because it's weight high up, you in fact get a reduced GM to begin with, but then because you pick up that buoyancy at probably 20 degrees angle, it actually is better than putting sponsons on. So as a general rule of thumb. So this gets you putting these stability boxes on the deck only, enables you to comply with the Marine Warranty Surveyor requirements for stability. But it is odd when you're not actually adding any buoyancy when it's in the normal case. You would think with the roll angles that we get on these vessels, which are quite low, they'll probably never ever get in the water. And again, used once and thrown away. Spend a few minutes looking at some incidents to do with barges and installation vessels, which makes us think about how we apply the marine warranty rules, regulations and guidelines. This wasn't carrying any offshore modules, it was a fuel barge, and you can see what's happened during the explosion. It's almost ripped the vessel completely in two. Overloaded the barge, probably a bit of corrosion in it somewhere as well, and it's bent in half. A fuel barge collision. It shows how it's been hit by a tanker and it's almost completely gone through the barge. Far more than the 1.5 metre penetration that we might have had. Yes, at the power and stern, yeah.
Yeah.
If you ever see any pictures of recent collisions between big vessels, particularly if it's a T-bone, it's far more than the 1.5, isn't it? And you also get the double penetration, the bulbous bow, and then the forecastle as well. It's very noticeable. Barge being towed with a few containers on, gets hit by a passing ferry. And you can see what's happened. It's knocked the cargo either damaged or knocked it off into the sea. So, for the ocean voyage part of these marine operations, we do look at damage cases of this type and damage into the hull. Capsized barge. It's really hard to capsize a barge. If you look at the photograph, it's obviously been there sometimes as somebody's cut a hole in the side and they're going inside from here. I don't know if you ever look at any pictures of capsized ships in recent years, but there's never any fouling on them. And I only wish I could get hold of the same anti-fouling paint for my boat, because that only lasts a few weeks, whereas you can see what here, typically, there's no marine fouling. Okay. Barge in Abu Dhabi, trailer loadout, all going well, people looking at it. Barge heels, module falls over into the sea and ends up in the water. 40 million pounds worth, $40 million worth of kit ruined. Probably what they've done here is they ballasted the barge, but then forgot completely about free surface effect in the tanks. Barge has got to this point, free surface effects have taken over, whack, over it goes.
Any normal stability software we can take that into account.
You don't need software, you just need to do the hand counts to do this. Yeah, and in fact that's the case with all these ships that have turned over capsized because of free surface effects. You don't need a computer, you don't need slide rule. A piece of paper and a hand cut will do it all for you. You don't need.
Oh, you see what happens.
Yes, which is
oftentimes actually software doesn't take into account free surface,
No.
especially if it's designed specifically to match the class society.
yeah. The free surface effect during loadouts, as I mentioned right at the beginning, is a real issue because the people dealing with this, you might not have a naval architect at the forefront of this. Probably he's done calculations, he or she's done calculations a month or two before, but the operation is done by people who don't understand that free surface effect. Somebody's just ballasted the barge to get it level and then not worried about the fact that each tank is half full.
Well, naval arcs are very expensive.
Yes. An 18,000-ton module. Classic case of the onshore pushers not telling the ballasting people what they're doing. There were link beams between the shore and the ship. They should have been free to move vertically, but somebody in their wisdom the day before the loadout welded them out. They had a ballast plan to work to, and as the module moved further onto the ship, they did the ballast plan in accordance with the procedures. But they'd over ballasted because these link beams were taking more vertical loads which they shouldn't have been doing. And eventually they broke, and the module began to slide away. And they were very fortunate that there were stoppers on the starboard side of the ship to hold the module, and they were fortunate that the seabed was shallow enough here to stop the ship turning any further. From people I know who were on board the ship, most of them jumped overboard. And it was like this for a day or two. You just look at this picture taken at night. Yes. As I said right at the beginning, for many of these offshore operations, it's all to do with misballasting and misunderstanding between different companies, different nationalities, people speaking different languages. An 8,000-ton module on a heavy transport vessel, travelling in Indonesian waters, struck an uncharted rock. Heavy transport vessel took on water, capsized, whole lot was written off as a total loss. $500 million worth in the sea, scrap metal. Sister ship to the one you've just seen, carrying a semi-submersible, ballasted down, semi-submersible floated off quite happily. Some misballasting here somewhere, and the heavy transport vessel just sank, as you can see. In this case, no fatalities. Semi-sub was fine. The ship was actually raised from the seabed and we've used it since. Yeah, just a simple bit of misballasting there. A geared heavy transport vessel lifting some cargo from ship to shore. Perhaps as not unusually, the cargo ended up was a lot heavier than they were told it was, and the vessel capsized. Just a few words in conclusion. You can see that there have been lots of accidents with these transport vessels, barges, heavy transport vessels. We do some unusual things in terms of the stability boxes, the sponsons, in order to increase stability to get just past the warranty surveyor guidelines. We have no guidelines, though, for the design of these temporary buoyancy stability tanks. My conclusion is that we should try to get some design methods for these stability boxes that would be easier to get past the marine warranty surveyors.